Okay, so in this project, we study visual data analysis on edge nodes. And particular, by visual data, we mainly mean by images and videos. And as a prototype implementation, we use a system for image processing on the edge called Diamond in this class. So analyzing images is not like analyzing text. When we analyze images, we usually use processing and algorithms in terms of filters. So for example, if we want to find vertical images with dots in it, we'll probably run two filters. One filter is to find all the vertical images, and the other filter is to find dots in the images with a deep neural network. So this is the basic architecture of the diamond system we're using. We perform searches in terms of filters, running filters. We have two projects here at CMU that targets image searches on the edge. The first one is a CMU urban video project, and the other one is the diamond system we talk about. Both these two projects make a strong assumption that the edge nodes, the compute nodes on the edge, have quite powerful processing power so that you can run all kinds of sophisticated computer vision algorithm on it. For example, the CMU Urban Video project have an NVIDIA Jackson's GPU, and the Diamond project have a NVIDIA GTX GPU on each of the machines. So, but in the future, we are seeing an increasing number of wimpy cloudlets. That means cloudlets with very weak processing power and have a very weak wireless link to the cloud. For example, we can imagine drones, body cameras wear by police officers. So all these cloudlets are very closely attached to the image source. However, they don't have the sufficient power to do very complicated image processing. For example, if you want to run a object detection, a face detection on a body camera wear by police officers, it will be very difficult. So in this project, we studied the system aspect of converging these two extremes. One extreme is you send all the data from the edge to the cloud to do all the processing, and the other extreme is you do all the processing on the wimpy edge node. So what we propose is to collaborate a powerful edge node with a wimpy edge node so that each edge node can do the filters that they are better at. This has the benefit of reducing the processing cost as well as minimizing the data transmission. So now we would like to introduce the system architecture.
This is our proposed system architecture, and the user will define some filters in the client application, and these filters will be offloaded to the Pervasive cloudlet. In Pervasive cloudlet, the scheduler will determine which filter will run in which places, and if we offload some filters to the wimpy cloudlet, we can gain the benefit of lower network transmission cost. And by doing the scheduler on the Pervasive cloudlet, we don't need to burden this overhead work to the wimpy cloudlet. And actually, we implemented the Diamond client server protocol, so it can extend the architecture recursively. It's not constrained to only these two layers. And for this scheduler, we support two kind of constraints, the hard constraints and the soft constraint. The hard constraint can support some flex, like could the GPU run 16 gigabyte and CPU capability. But only this hard constraint is not enough. We should have some soft constraints to sort the filters which all satisfy one hard constraint. The soft constraint can optimize for the end-to-end drops per second at runtime. And currently, our implementation will use some statistics given by the Oracle. And in future, we can extend them to use the history database or inference from the historic research.
Okay, now we can look at some experimental results. So this graph shows three groups of experiments. The first group of experiments runs a very cheap filter that's called the vertical filter. That means just to find out the vertical images out of all images. So as you can imagine, this filter is very cheap. It takes very little time to run. So what happens is that if we run it if we run everything on the WinP cloudlet, the speed is the best. So the y-axis here shows the number of jobs per second, which is higher the better. That's the WinP is best in this case because the WinP's limited processing power is sufficient to process this data at a high enough speed, and at the meantime, only the necessary data is sent from the WinP cloudlet to the BV cloudlet for processing. So the wireless network transmission cost is reduced to the minimum. The second group of experiments is about an deep neural network filter. This is just the opposite of the vertical. Running a deep neural network is very expensive and resource consuming. So again, if we run the deep neural network on the WinP cloudlet, you'll see its performance is very bad. So instead, if you run the inception on the BV cloudlet, the speed will be much better because the BV cloudlet has much more powerful memory space and CPU. And finally, if we put the vertical filter and the inception filter together, we will see this graph. If you run both filters only on the WinP, you get very bad performance because the WinP cloudlet's CPU is too weak to run the deep neural network. On the other hand, if you put both filters on the BV cloudlet, you also get pretty slow speed because all data are sent from the WinP to the BV cloudlet before it is processing. And that will saturate the weak wireless link between the WinP and the BV cloudlet. So the sweet spot between these two extremes is to just run the cheap vertical filter on the WinP cloudlet and run the expensive deep neural network on the BV cloudlet. In this way, you reduce the number of wireless transmission by a significant amount, and at the same time, you can utilize the powerful CPU on the BV cloudlet to speed up the calculation of the deep neural network.
Okay, this is the runtime breakdown at the mixed workload here. So the vertical axis here is the jobs per second, and the vertical axis here is the time. And this is the runtime breakdown of this case. And from this graph, the first we can say is the most time consumed in BV cloudlet is the yellow one. So this will include the network transmission or the waiting time at the BV cloudlet. So we can say this takes longer time than the offload mode because it will waste a lot of time to waiting for the result from transmitted from the WinP cloudlet. And the next thing we can say is in the WinP, the time breakdown of the WinP cloudlet, there is most of the time we're spent on the inception filter. That means the WinP is too weak to process the inception filter, and the offload mode will take the least time because it will gain the benefit from the minimal transmission cost, and it will also gain the benefit from the powerful BV to reduce the inception processing time. And these two graphs will show the influence of different factors. This graph will show the influence of the job ratio. That means how many images will be dropped from this filter. And the left saddle bar is the vertical and inception. The right saddle bar is the horizontal and inception. So the only difference So the filters are same, but the only difference is this use the vertical and this use the orient, oriental, orient, horizontal. And in the vertical, it will pass less images than the horizontal filter. So we can see we can get more benefit because this will trans less images from the WinP to the BFIC quality.
So the last factor we explore is how costly to run the particular filter and how this cost affects the performance trade-off between the WinP and the BV. So for example, if we compare the first group and the second group of experiments, we changed the very expensive of the deep neural network to a less expensive RGB histogram. So when the expensive filter becomes somewhat less expensive, actually the performance of the WinP only approach will increase because now the WinP CPU can still run the less expensive filter at a fair speed. And on the other hand, if we add on, if we add in another filter, which is the shift keyboard matching filter, which is again less expensive than the deep neural network, we see this makes the performance difference between the WinP and the BV approach converges. So basically, when the cost of the filters is not so radically different, the performance gap between these two extreme approaches will converge, and the performance gain of the collaborative approach will shrink accordingly. That's it for our project demonstration. So here it shows running one single search using the three different approaches. So in here, we are trying to find all vertical images with a dot in it. So as I said, this requires two filters. One is a very cheap vertical image filter, and the other is a very expensive deep neural network filter. So you can see on the left-hand side is the two extreme approaches. You run everything on the BV cloud, but you are streaming all the data from the BV to from the WinP to the BV before you can process them. And on the WinP only approach, you do everything on the WinP cloud. So you can see the speed of both of these base 9 approaches is not as far as our method, which process the vertical image filter on the WinP cloud and process the expensive deep neural network filter on the BV cloud. Because in this approach, it both reduces the wireless transmission between the two clouds and reduce the computational burden on the WinP cloud. We have put all our results and materials and posters on the website. You are welcome to scan this QR code to go get to our webpage. Thank you.